Okay, hello. This is just a quick video to explain a couple problems that I've had some questions on. So the first one is this question: what is the area under p equals 50 times 0.7 to the power t from t equals 0 to t equals 9? And you can do this in one of two ways. The first way is to sort of reverse engineer. Well, first of all, actually, what we want to do here ultimately is the integral from 0 to 9 of the function 50 times 0.7 raised to the power t dt. And one method is to reverse engineer the fact that the derivative of a to the x is a to the x times ln of a. So just like the same situation with the e to the kx rule, when we want to do the indefinite integral of a to the x dx, we are going to get a to the x divided by ln of a instead of multiplied, okay, plus c. The second method is to recognize that a to the x is the same thing as e to the ln of a, all being raised to the x power, in which case the integral of e to the ln of a, which if we multiply these two powers together we get ln of a times x, then we can use the e to the kx rule to find this antiderivative, which will just be e to the ln of a x times divided by ln of a, right? So divided by ln of a, and this can also be rewritten as a to the x over ln of a. So two different perspectives on finding this antiderivative. So to do it for our specific case, we pull the 50 out, integral 0 to 9, 0.7 raised to the power t dt. So we just apply this rule here, which says we're going to do 50, and then we have 0.7 raised to the t divided by ln of 0.7. And we need to evaluate this at 0 and 9. So I moved everything to the right-hand side to show that now I've done the antiderivative, and now all that's left to do is plug in. So we get 50 times, and now I need to plug in first 0.7 to the 9 divided by ln of 0.7, and then we need to subtract from this 0.7 to the 0 divided by ln of 0.7, and that should, if we evaluate this correctly, this should get us the correct answer. Okay, so for the next one, it was regarding the ice problem from the homework. So we have that the ice is growing at a rate of square root t over 2 inches per hour. So we're supposed to estimate the thickness of the ice after 13 hours. So what we can do here, and let me move this one down. So what we can do here is recognize that what we're asking something about the function t of t, which represents the thickness at time t. So to find out what that function is, we know that it's going to be related to the rate at which the ice is growing, right? The thickness of the ice changes according to this rate function. So we know we have the relationship t of t is equal to r prime of t. So this is kind of like the problem we did in class where we were talking about the temperature of a coffee cup going into like a cold room or something like that. Okay, so we know we have this, but in order to find out what is the unique function t through this antiderivative process, we also need to have this additional piece of information, which we can infer from the problem that t of 0 is 0. So why can we infer that? So first of all, just the way the problem is written, it does make it seem, to me at least, like there is no ice at the beginning, but also you can recognize that when t is equal to 0, the rate at which the ice is growing is 0, which is to say that there's no ice growth at time 0, So it's, you could argue that it's a leap to say that there was no ice growing before, but that's just maybe a small flaw in the problem. But let's work through this under these assumptions and see if we can figure out what the function t of t is. So we know that we can do the integral of square root t over 2 dt, and that will give us 1/2 times the integral of t to the 1/2 dt, which we can do using the power rule, will give us 1/2 times t to the 3/2, and we need to divide this by 3/2, and plus c. So this becomes 1/2 times 2/3 times t to the 3/2 plus c, which is just 1/3 t to the 3/2 plus c. And so we've used up sort of the first piece of information which we have, and now we need to use the second piece to figure out what is the c going to be. So to do that, we just say that t of 0 is what we get when we plug in 0 into this function, which would be 1/2 times, or 1/3 times 0 to the 3/2 plus c is equal to 0. And this tells us, since the first part is 0, that c has to be 0. So the full function t of t, the unique antiderivative in this case, is going to be just 1/3 t to the 3/2. So in order to find out what is the thickness after 13 hours, now that we have the function which describes the thickness after t hours, we can just plug in 13. So t of 13 would be equal to 1/3 times 13 raised to the 3/2 power, and that would be our final answer for this part. So for the second part, I think some students have been confused because they feel like it's asking more than it really is. But remember, it's asking us what is the growth rate of the ice at t equals to 13, or at what rate the thickness of ice is increasing after 13, right? This is going to be given by just plugging in 13 into our rate function. This rate function tells us how fast the ice is growing. So we can just plug 13 into that, so that would be r of 13, which would be the square root of 13 divided by 2. Okay, so I hope that this helped explain these two problems. So this one, essentially, the first part was an initial value problem, and the second part was just plugging into the derivative. And then for this other problem, just a slight modification of an e to the kx rule. So you could use either of these two methods to try to solve that one. So I hope that helps, and have a good day.